In our previous trig unit, we occasionally dealt with sines and cosines of angles that were bigger than 90, which means those angles could possibly come from right triangles. And at the time, we didn't say much about it, kind of just trusted the calculator and went forward with things. But it's time to now figure out how exactly do you deal with sines and cosines of angles that can't possibly have come from right triangles because they're too big. Let's do a little calculator practice here. So on your Desmos or on your handheld calculator, make sure you're in degree mode for these. And I just want to make sure that you can get the same numbers that I'm getting. So for example, I type in sine of 100, I get an answer out. That's the first thing I want you to know. These things are defined, they do exist. And make sure you get the same numbers as me. So here, I'm going to have about 0.9848. Let's just go to 4 decimal places all the time. How about sine of 180 degrees? Oh, that's interesting. Sine of 220 degrees. Oh, it's negative this time. Negative 0.6428. So something's going on because I've got a sine of 0. I've now got a sine that's a negative number. Let's see what else happens here. Sine of negative 50. Can you even do a sine of a negative angle? Yes, you can. I ended up getting this time another negative number. That won't always happen, but it will sometimes. Now 450. So think about how we're doing our angles. That's all the way around the circle. And then another 90 degrees. So the sine of 450 degrees, interesting again, ends up being just the number 1. And sine 2718. So that's lots of times around the circle. And then a little bit extra. Let's see where we end up. Another negative 0.3090. Okay, so somewhere along the way, mathematicians must have decided that to do a sine of an angle that can't possibly have come from a right triangle, there is a method. Otherwise, we wouldn't be getting these numbers. Our goal is to understand what that method is, and it comes from right here. We're going to start off by doing sines and cosines the way that you've always done them, and that is by looking at a right triangle. We're going to focus on this graph. So this is our x-axis and y-axis, x across, y up and down, and then a circle drawn in. And what we're going to imagine is an angle that we're going to call theta right in here. Now that angle theta is going to make a terminal side. So here's the initial side, here's the terminal side. And notice that this terminal side of the angle hits the circle right up here. We're going to use that intersection to create a right triangle. Just like this, right angle, and just like this. So we've got our angle. We have now made a right triangle. Let's now think about the sine, the cosine, and the tangent of this particular angle based on opposite, adjacent, and hypotenuse. So from the point of view of this angle, the hypotenuse, that's always the long side that's across from the right angle. This is my hypotenuse. From the point of view of this angle, go directly across to the opposite side. And then the remaining side that touches theta and the right angle, that is our adjacent side. Now here's what I'm going to do. I want to set up here my trig ratios. So the sine of theta, well, that is my opposite over hypotenuse. And the cosine of theta is the adjacent over the hypotenuse. And actually, we're going to hold off on tangent for later. Let's just look at sine and cosine here. Now, here's what we as mathematicians have said. We have said that it doesn't matter whether this is a very, very big triangle or a very, very small one. As long as the angle is the same, these trig ratios are also always going to be the same. So I don't know about you. I like to avoid division in fractions if I can help it. So let's think for a moment. What number could I put in down here for hypotenuse, where if I divide by the number, it doesn't change anything, and so we don't need it? Hope you came up with what I came up with. 1. If you divide by 1, nothing changes. We're going to define this hypotenuse length to be the number 1. If I do that, then this becomes opposite divided by 1, just opposite. This becomes adjacent divided by 1, which is just adjacent. And it gets even better than that. Think about this. If we recognize that, hey, the adjacent side here, well, that's just the distance from the origin sideways to this red point up here. That's the x-coordinate. Well, then the adjacent side just has the same length as this x-coordinate. If we do the same thing vertically, well, the opposite side length, that's just down here from the x-axis up to this point. That's just the y-coordinate. We have now made calculation of a sine and a cosine very, very simple. I want you to open up in the canvas. There's a link to a Desmos sketch called the unit circle, and it should take you right here. Here's a circle with a radius of 1. Here is our angle theta. Now, in Desmos, I had to call it A because if you type theta, other things happen. And I've set it up so that you can move this and you can see, okay, as I go, the triangle changes. I got that. The coordinates here of this point also change, so it lets you know where you are. All I want you to do is compare for this angle, which now I'm measuring in radian. Important to know. I've got Desmos set to radian measure here. So this angle, measured in radian, is about 1.026. When I extend the terminal side of that angle to the unit circle, it intersects at this point, 0.518 and 0.8552. Take a look at what the cosine of A is, 0.518. Take a look at what the sine of this angle A is, 0.8552. That's not coincidence. No matter what angle you pick here, the cosine and sine will always be the same as the x and y coordinates of this point on the circle. Here is how mathematicians have decided to define sine and cosine. The sine of an angle, well, actually, before we get there, I want to make sure we understand what the unit circle is. It's just a circle. It's centered at the origin with a radius of 1. And again, the reason we chose that 1 for the radius was to make these divisions easier to do. Now, back to that discussion we were having about sine and cosine. So here's what it means. The sine of an angle now has a new definition. We're defining it as the intersection. So when you draw an angle's terminal side, it will intersect the unit circle. The y-coordinate of that intersection is that angle's sine. The x-coordinate of that intersection is the angle's cosine. Here's why that's helpful for us. It allows us to extend not just to right triangle angles in the first quadrant. It's now going to allow us to extend to angles that can't come from right triangles. Like this red angle right now, this theta, it's bigger than 90 degrees. It's more than pi over 2 radian. Nothing's changed. We can still make a right triangle. We can still look at this point up here. It's got an x-coordinate. There's your cosine of this angle. It's got a y-coordinate. There's your sine of this angle. Notice that now because we're on the left, the cosine is a negative number. That's how you can get a cosine that's negative. If we keep going, so now I've got an angle that's even bigger than 180 degrees, bigger than pi radian. Now, because I'm in quadrant 3 here, I'm at the left, the cosine is a negative number. But because we're down below the x-axis, the sine is also a negative number. We're defining the sine and cosine of this angle, 3.88 radian, to be the coordinates of this intersection, which this time are these two numbers. You can continue that around. Here in quadrant 4, now I'm to the right, so my cosine is a positive number. I'm down below the x-axis though, so my sign is a negative number, and there you go. And around the circle you can go, just like that. It doesn't matter if you go backward, doesn't matter if you go around the circle several times and end up somewhere. The definitions of sine and cosine are the same. It's the coordinates of the point of intersection of the terminal side of the angle with the unit circle. Cosine is the x, sine is the y. Couple of important things that I want you to know. The magnitude, meaning the number that you get for your sine and your cosine, is determined by the reference angle. I'm just going to sketch an example over here on this circle. I encourage you to do the same thing in your notes. Let's pick an angle how about in quadrant 2? So I got an angle, I'm just going to make it go something like this. So here's my angle theta. That's going to give me a terminal side. I'm going to extend my angle to match my terminal side. There we go. And therefore an intersection right up here. There's my x and my y. There's the cosine of this angle theta, and there is the sine of this angle theta. I'm even going to write it that way. Cosine of the angle theta is the x coordinate. Sine of the angle theta is the y coordinate. The numbers are the same as the sine and cosine numbers you would get if you looked at this angle, the reference angle. So from the previous portion of the lesson, you remember calculating those reference angles? Well, what you will find is if you do the sine and the cosine of this angle theta, you're going to get the same numbers as the sine and the cosine of this little blue angle right here. Now, the positives and negatives might be different, but the size of the numbers will be the same. And that's true no matter what quadrant you're in. Now, speaking of quadrants, this is where you get the signs, the positives and negatives of your sine and cosine values. Think about your first quadrant, quadrant 1. You have x's being positive and y's being positive. So if you have an angle that ends up in quadrant 1, your sine and your cosine are both going to be positive numbers. In quadrant 2, well, over here, the x's are negative because we're to the left of the y-axis, and the y's rather are positive because we're above the x-axis. So in quadrant 2, your cosines are going to be negative numbers, but your sines are going to be positive numbers. Let's continue on. In quadrant 3, if we put a point down here, well, that would mean that I'm going to have a negative x because we're to the left of the origin. I'm going to have a negative y because we're below the origin. For an angle in quadrant 3, I'm going to head back here to the sketch real quick. The sine and the cosine are both negative numbers. And then lastly, in quadrant 4, put a point over here. It's to the right of the origin, so the x's, the cosine of that angle will be a positive number. The y's, the sine of that angle will be a negative number. And as we look at our unit circle, put an angle in quadrant 4, and sure enough, the cosine is something positive and the sine is something negative. This, my friends, is going to take a while to become comfortable with. So I want you to experiment. I want you to use your calculator and do some sines and cosines. See if you can figure out before you press the enter button whether you're going to get a positive answer or a negative answer. It's going to be great practice for you all around. Now, let's summarize here. So cosine is positive where x is positive. Remember, the definition of a cosine is an x coordinate on the unit circle. So that's going to happen in quadrants 1 and 4. That's going to be my quadrant here, and here the ones that are to the right of center. For sine, sine is positive where the y's are positive. Make this connection and this connection very clear. That needs to be ingrained in your brain. Cosine is x, sine is y. Y is positive above the x-axis, which is in quadrants 1 and 2. Now there is one final bit here that I want to include with this unit circle discussion, and then we'll wrap this recording up. A direct consequence of defining the sine and cosine the way we have in the unit circle is what's called the Pythagorean identity. And it looks a little bit like this. When you put an angle, let's use this theta again as an example, in the unit circle, you always get a right triangle. We know that in a right triangle, a squared plus b squared equals c squared, right? Well, let's come down here and see what we've got. A squared plus b squared equals c squared. In the unit circle, though, the a, the b, and the c, well, those have very specific meanings. The a is the adjacent side length. That's my x value. Well, that's the cosine of the angle. Okay, so that means that the cosine of the angle squared, that's my a squared, added to, let's move over here, the b squared, well, that's just the opposite side length. That's my sine of the angle. Okay, so plus the sine squared equals c squared. Well, c is the hypotenuse length. In the unit circle, we defined the hypotenuse length to be the number 1. And 1 to the second power is just 1. This is called the Pythagorean identity, and your pre-calculus teacher is going to expect you to know it. Cosine squared plus sine squared equals 1. You'll sometimes see it written this way. You may also see it written this way. It means the exact same thing. Sometimes, just to avoid using the parentheses, mathematicians will write the squared right after the word cos, or right after the word sin. That means you're squaring the whole cosine theta, you're squaring the whole sine theta, and together those are equal to 1. So here's what I want you to do. Play around with this. Talk with your friends about this. You may want to look at the Khan Academy on this, because the better you understand the unit circle, the better set up you're going to be for everything that comes after.